We were talking about a heavy symmetric top last time, and this top was supposed to be having a fixed point, which is its lowest point as well. And last time we defined a variable u, which was cos of theta, where theta gives you the inclination of the axis of the top with respect to the vertical direction. So in this problem you have a direction because of the presence of gravitational force, which we have taken to be uniformly pointing downwards. Okay, so imagine your top to be being put on the surface of the earth, okay, and you are treating the field to be uniform. So that's what we did last time, and then with this definition or definition of u, we could write down the energy conservation as the following equation. So we could convert our energy conservation equation to u dot square is equal to f of u. Okay, and this was equivalent to one dimensional problem. Okay, and here our f of u we found out to be found out it to be alpha minus beta u 1 minus u square minus a minus b u whole square. Okay, that's what we found. Let's go back and see somewhere here it should be. Okay, and also you see that beta is positive. You have 2 mu g L over I1 prime. Okay, so beta is positive. Let's return. Okay, that's good. And also let's go back and see that we had written down an equation for, I believe, phi dot somewhere. Yes, so we have a phi dot. Okay, that's what we wrote, and this time derivative of phi can again be written down in terms of constants a, b, alpha and beta. Okay, if I plug them in that expression of phi dot, I will get the following: phi dot is equal to a minus bu over 1 minus u square. Okay, you can verify this, so it's trivial algebra. Okay, that's good. Now let's ask how the inclination of the top changes with time. Okay, or we will not answer how it really changes in time, but we want to know at least some information about the inclination of top, which is encoded in this relation u dot square is equal to f of u. So let's look at it. Inclination theta of the top. Okay, remember, let me go to the figure here. This is the inclination. Okay, that's the theta, and this is the z direction. So right now we are asking about this angle. Okay, very good. So let's see. So first of all, the physical motion will happen in the range -1 to 1, because cos theta can take values here. Let's go back. Theta could be 0 or theta could be pi. Okay, so it happens between u equal to 1 and -1. So that's what let's write down. So point number 1 is the physical motion it happens in the range -1 to 1 for the variable u, okay, which corresponds to theta equal to 0 and theta equal to pi. Okay, that's one piece of information we have. Now Another thing you note that f of u is polynomial of degree 3. So you see you have a beta u which is multiplying a u square, which makes it beta cube, and it's the highest power you get for u. So f of u is a polynomial of degree 3. Okay, that's good. And the turning points, you see, we remember we are having the same thing as we had in the case of two-body problem. So as far as the equations are concerned, it looks the same. So the turning points, meaning the place where u dot will go to 0, okay, is given by f of u equal to 0. Okay, so the equation f of u equal to 0 gives us the turning points. Okay, there the turning points were in r, here the turning points are in theta, which basically tells you what will be the maximum theta and minimum theta which are allowed for this top. Okay, what is the minimum inclination it can make and what's the maximum inclination it can make. Okay, that's good. Now f of u equal to 0 is a cubic equation, and you know from the fundamental theorem of algebra that this will have 3 roots in general. Okay, so let me write it down. So your fundamental theorem of algebra tells you that there are 3 roots for the equation f of u equal to 0. Okay, we'll try to see whether, see, the roots are in general complex, so it's not guaranteed that your roots will be real. Okay, so one has to, and if the roots are not real, then it doesn't directly apply to your problem, because your problem is happening in the real space, so the cos theta or the theta has to be real. So that's why we need to think a little bit more. Now, from whatever information we have available here, we will be able to make conclusions which are sufficient for our purpose. So first thing we note is that maybe here, if you look at f of u and take u to be very large, okay, then the cubic term will dominate, okay, because that's the highest power you have, so it will be the leading term. So for large f of u, for large u, f of u behaves as beta u cube, and remember that beta is greater than 0. So it basically blows up in the positive direction. So which means if you take the limit f plus infinity, okay, you get infinity. Okay, that's one information we have, which is going to be very useful. So let me go and start drawing a diagram which will make things appear simpler. So here, okay, maybe just a second. If I take this, it will be easy. Perfect. So this is my u direction, okay, and let me take this here and we'll make this as our f. So y-axis or the vertical axis, I'm plotting f of u, okay, and here you have u. So what I have said is, for very large values of u, as you are going towards this direction, your function is going to blow up. So it will be something like this. Okay, it is going to blow up. This is just generic. Don't take seriously this straight line kind of thing. It just has this behavior. Okay, so that's one thing we have concluded. Second, let's evaluate what the values f takes at the boundaries of physical region. Okay, the physical region is bounded between -1 and 1. So in the physical region, at the boundaries, if you evaluate f of +1, this you see put +1 here, or even if you put -1, because of this term it will become u square is 1, so this will go away, it will give you 0, which means first term will not contribute and only the second term will contribute. Okay, and it will be minus of a minus b square, which is negative because of this sign, and f of -1 will also be negative because there is a minus sign and you have a square of two real numbers. Okay, so in either case you get a negative value. Okay, that's good. So let's go back to this figure and draw somewhere here a +1 and a -1 here. So what we have concluded is that in this region, okay, let me try again. Okay, so here it should take some negative value. So let me just put something generically. Some negative values it will take, and I'm not really bothered about what the values it takes. Okay, okay, that's another thing we have concluded. Yeah, now third thing, which is going to really fix everything for us, is that because our u dot square is positive, it's a square of a real number, so it has to be positive, which means that f of u must be positive. Let me write down, must be positive in some interval between -1 and 1. Okay, must be positive in some interval this. Okay, because otherwise there will be no solution. Otherwise there is no solution possible. So it has to be positive somewhere. Okay, because u dot square is positive, so it has to be at least in some interval. Maybe not the entire interval from -1 to 1, but in some interval it should be positive. Okay, otherwise nothing makes sense. So which means that in this interval, okay, somewhere f of u should become positive. So it should be above this horizontal line. Okay, now my function is negative here, it goes to infinity here at very large values, and then it should definitely come down to negative. Okay, because it has to be negative at u equal to +1. So at this point it has crossed the horizontal axis where f of u equal to 0. So this is first root, right? And this I know will happen because it has to come down to here. But then I know that it has to become positive somewhere in the region. So it has to go up. And because it has to again go down because it has to reach this point, I expect something of this sort. Okay, which means I have 3 real roots of this. Okay, so let's call this u1, which corresponds to value θ1, and this u2, which corresponds to value θ2. Okay, so what I've concluded is that there are 2 real roots, in the physical interval. See, this one is not in the physical interval, it is outside the range -1 to 1. So in the physical interval, Okay, that's good. And these two will correspond to values theta 1 and theta 2. Okay, which means that as the top moves, the axis of the top is going to periodically change its inclination. Okay, and it has to periodically move between theta 1 and theta 2. Right? So let me go back to this figure, which means as the top is moving, whatever it is doing, this axis will keep going down and up between some theta 1 and some theta 2. Okay, so it will keep going up and down like this, in addition to whatever it is going to do, which we are going to talk now in more detail. Okay, that's nice. And this motion of the axis going up and down is called nutation. So let me write it down, that part also. So what we have concluded is that the axis of the top is going to periodically change its inclination okay, remaining between theta 1 and theta 2, always remaining, but it will always remain between theta 1 and theta 2. These are the limits. Okay, and this is called nutation. Let me try to get some color. This is nutation. Okay, TATION. Perfect. So so now you know three things about the tops. One, they spin about their axis, of course. Then you saw, even in the case of freely moving top, freely moving symmetric top in space, okay, it was precessing. Now you have come across a new phenomena, which is nutation. So in the case of free top, the angle was always fixed. It was not changing. But here you see that the angle will also change between theta 1 and theta 2, and this is called nutation. Okay, that's good. Let's talk more about now the azimuth of the axis. Okay, so we have an equation for phi dot, which tells you about the azimuth. Azimuth. Let's go here. This one, right? So this is giving you the azimuth of this axis of the top. Okay, and this is what we want to know now. See, we are not going to solve in detail the entire motion of the top, nor we are interested in. I'm not so keen on knowing what will be the value of theta 1 and what will be the value of theta 2, given the parameters we describe this top. I'm fairly happy in knowing that the motion is such that the inclination is going to change with time, and it will remain between these two. Okay, and let's make some study of theta dot now. Okay, azimuth. So let me see here. Inclination theta of the top, that's what we did. Let me write here itself nutation. Okay, now we go. Okay, here. Maybe to the next page. Yeah. So now we are interested in azimuthal motion of the top. Okay, I'm just interested in how its axis is moving. And as you already know, you have encountered this before, this is called precession. Okay. That was the precession. So let's look at this. Our phi dot, we have already already written down that it is a minus bu over 1 minus u square. Now there are three possibilities. One is that the phi dot is 0 outside theta 1 and theta 2 interval. So outside the interval, I mean the value of theta or the value of u for which phi dot is 0 lies outside the interval theta 1, theta 2. So let me write it down. So there are three possibilities. So first possibility I have already described. Phi dot is equal to 0 outside theta 1 and theta 2. Okay, and this theta 1, theta 2 is what we talked about in this context, in the case of nutation. Now there is a second possibility that phi dot is equal to 0 inside this range. Okay, and the third possibility is it is on one of these. Phi dot is equal to 0 on either theta 1 or theta 2. Okay, so these are only three possibilities. And all these possibilities correspond to a minus bu equal to 0, and you solve this numerator, this equal to 0, and you solve it, and your solution gives you one of these possibilities. Okay, that's what we are talking about. Now to geometrically visualize what is happening, what I'll do is I'll draw a unit sphere with the center at the origin, and origin is, as you recall, at the tip of the top. Okay, here. So we are imagining that I'll draw a unit sphere around this, taking this as a center, and then what I want to look at is where this axis, x3 axis, cuts the sphere. So it will pierce through the sphere at some point. Okay, and what we are asking is how that point moves as the top moves. Okay, so it will give you a visual picture of how the axis is moving around with time. Okay, so that's what we want to describe now. Okay, very good. So I will do the following, maybe here itself, just a second. Yeah, so let me draw a circle, not a circle, a sphere. Yes, it's better I don't do a freehand drawing, otherwise it will be okay. No, not this, a circle. Oops, no. Yeah, okay. And then because there are three cases, let me draw three circles. I'm not sure whether I'll be able to draw them equally of equal radius, but anyhow. No. No. Okay. Anyway, these are all the same circles, so even if they look different, we can pretend they are all same. So let me, so you have a, no, what is happening? Let's go here and remove this. Perfect. So let's look at the possibility number 1, that theta dot is outside this interval. So let me first draw. So here is your direction of z, okay, because this direction is set by the direction of your gravitational force. And then let's say these are your theta 1 and theta 2 values. Okay, that's good. Now let's say my theta, which gives phi dot to be 0, is outside this interval. Okay, so that, let's say that theta corresponds to something here. Okay, theta 1, theta 2. Okay, now imagine that your top axis is piercing this thing somewhere. Okay, and it will be, of course, within this band of theta 1 and theta 2. Okay, now let's look at possibility 1. So as time goes on, the theta 1 and theta 2, I mean the inclination will keep periodically changing between theta 1 and theta 2. Okay, that you already know, just like in the case of your two-body problem. Okay, the radius vector was changing between its and how did you say that, its limiting values of minimum r and maximum r. Okay, turning points. So here it will be the same, and then phi dot. Okay, so phi will keep changing with time. So the possibility 1 is that let's start from here. So phi is increasing. Okay, so this is the place where the axis is piercing this sphere. Okay, imaginary sphere. So here the axis is crossing, and then value keeps increasing. Okay, keeps increasing. Okay, so this has this kind of behavior. It doesn't come out very nicely. Okay, so this is how the tip of not necessarily the tip, the axis of the top will carve out shape on this unit sphere. Now let's go to the second case where phi dot is 0 somewhere between this region. So let me first draw. This is my z. This is theta 1 and theta 2 region. Theta 1, theta 2, and I'm saying somewhere here I have a solution of phi dot equal to 0. Okay, so phi dot goes 0 somewhere here, which means, let's say I start like this. So the particle is the axis is going, it's increasing in its value of phi, so azimuthal angle is increasing. Okay, it's increasing, but here when it reaches at this point, the rate becomes 0. So let me do it again. It becomes 0, so it has to become like this, and then because it became 0, after that it has to change sign, right? So it changes sign. So here the derivative is 0 at this point, and that's why you get this slope to be 0 if you view it with respect to theta. And then it has to become negative, but then after a while it touches the boundary and it has to come like this. Okay, the same thing repeats. Goes, slope becomes 0 at this point, then the direction of phi becomes opposite, and then it goes again like this. Okay, so that's the way the top is going to, the axis of the top is going to move. It will make loops. Then the third option is that phi dot is 0 either on theta 1 or theta 2. So let me draw it again. Not very nice. Let's do it again. Okay, this is theta 1, this is theta 2. Okay, and let's suppose that theta 2 is the place on which phi dot is going to 0. So let's say the derivative goes to 0 on this arc. Okay, so what's the situation now? So your tip will move like this. Okay, it returns, it goes up. Okay, now the derivative has to vanish here, but your higher values of theta are not allowed, so it has to return back, and this is what you'll get. So it makes cusps here. So it continues in this manner, where this was the z-axis. Okay, so let me write down. Yeah, so all these correspond to your a minus b u equal to 0. Okay, and what we have done here is it's the intersection of the axis of the top with unit sphere. It's a nice way to visualize what the top is doing. Okay, so this is quite nice. So in addition to your spinning about its axis, the top also precesses, which we saw earlier in the free case, and then in this case, with gravity being there and the top being heavy, we saw that there is also a nutation. And if you look at the axis of the top, it's making this these nice kind of motion, and there are three possibilities, and one of these is going to be realized in your top. Okay, so I think this is really nice that we can, without solving any equations, we have not solved any equation. You see, we have not done any quadrature. We never tried to solve theta or phi or anything with as a function of time. We didn't do any integrals. We didn't solve any equations of motion, purely based on the first integrals which we derived or which we obtained by the symmetries. Okay, we looked at some cyclic coordinates, and knowing those cyclic coordinates, we could arrive at, or rather informative picture of what the top does as it moves around in time. And of course, I have not derived what are the values of theta 1 and theta 2 as a function of the parameters, okay, and all other details. But yeah, who cares? We if we wish, we can derive, but we are at the moment not so much interested in those details. Okay, so it's nice. We'll continue a little more on tops in the next video.